Lying just beneath everyday reality is a breathtaking world where much of what we perceive about the universe is wrong. Physicist and best-selling author Brian Greene takes you on a journey that bends the rules of human experience.
Why don't we ever see events unfold in reverse order? According to the laws of physics, this can happen.
It's a world that comes to light as we probe the most extreme realms of the cosmos, from black holes to the Big Bang, to the very heart of matter itself.
I'm gonna have what he's having.
Here, our universe may be one of numerous parallel realities. The three-dimensional world may be just an illusion, and there's no distinction between past, present, and future.
But how could this be? How could we be so wrong about something so familiar?
Does it bother us? Absolutely.
There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a game-changing perspective that opens up a whole new world of possibilities. Coming up,
What if you took all this stuff away?
we're left with empty space. But what seems like nothing is actually teeming with ferocious activity. What is space?
It is one of the deepest mysteries in physics.
Could its elusive ingredients hold the key to the fate of the universe? The fabric of the cosmos, right now on Nova.
Major funding for NOVA is provided by the following: David H. Koch and
Discovering New Knowledge. HHMI.
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Major funding for the fabric of the cosmos is provided by the National Science Foundation, where discoveries begin. And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. Additional funding is provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education. The U.S. Department of Energy's Office of Science, and the George D. Smith Fund.
We think of our world as filled with stuff, like buildings and cars, buses and people. And nowhere does that seem more apparent than in a crowded city like New York. Yet, all around the stuff that makes up our everyday world is something just as important, but far more mysterious. This space in which all this stuff exists. To get a feel for what I'm talking about, let's stop for a moment and imagine. What if you took all this stuff away? I mean all of it. The people, the cars and buildings, and not just the stuff here on Earth, but the Earth itself. What if you took away all the planets, stars, and galaxies, and not just the big stuff, but tiny things down to the very last atoms of gas and dust? What if you took it all away? what would be left? Most of us would say nothing, and we'd be right. But strangely, we'd also be wrong. What's left is empty space, and as it turns out, empty space is not nothing. It's something. Something with hidden characteristics as real as all the stuff in our everyday lives. In fact, space is so real, it can bend. Space can twist. And it can ripple. So real that empty space itself helps shape everything in the world around us and forms the very fabric of the cosmos.
Well, you can't understand anything about the world unless you understand space, because that's the world. The world's space with stuff in it.
We're not usually very conscious of space, but then again, I tell people fish are probably not conscious of water either. They're in it all the time.
Space is not really nothing. It actually has a lot going on inside.
When most of us picture space, we think of outer space, a place that's far, far away. But space is actually everywhere. You could say it's the most abundant thing in the universe. Even the tiniest of things, like atoms, the basic ingredient in you and me and everything else we see in the world around us, even they are almost entirely empty space. In fact, if you removed all the space inside all the atoms making up the stone, glass, and steel of the Empire State Building, you'd be left with a little lump about the size of a grain of rice, but weighing hundreds of millions of pounds. The rest is only empty space. But what exactly is space? I can show you a picture of Spain, of Napoleon, of my Uncle Harold. But space, it looks like this. Nothing. So how do you make sense of something that looks like nothing?
Why is there space rather than no space? Why is space three-dimensional? Why is space big? We have a lot of room to move around in. How come it's not tiny? We have no consensus about these things.
What is space? We actually still don't really know.
It is one of the deepest mysteries in physics.
Fortunately, we're not completely in the dark. We've been gathering clues about space for centuries. Some of the earliest came from thinking about how objects move through space. To get a feel for this, take a look at that skater. As she glides across the rink, she's moving in relation to everything around her, like the ice. And when she goes into a spin, not only can she see that she's spinning, she can also feel it. Because as she spins, she feels her arms pulled outward. But now let's imagine that you could take away all the stuff around her, from the rink to the most distant galaxies. So the only thing left is the skater spinning in completely empty space. If the skater still feels her arms pulled outward, she'll know she's spinning. But if empty space is nothing, what is she spinning in relation to? Imagine you're that skater. When you look out, you don't see anything. It's just uniform, still blackness all around you. And yet, your arms are being pulled outwards. So you say to yourself, what could I be spinning with respect to? Is there something out there that I'm not seeing? Trying to answer questions like these, scientists came up with a bold new picture of space. And the key was to make something out of nothing. When you go to the theater, you watch the actors.
I do confess that I love nothing in the world so well as thee.
The scenery, the story.
But I protest, I love thee.
Well, then, God forgive me.
What offense, sweet Beatrice?
But there's something important here that you won't find mentioned in the playbill. something we hardly ever notice. The stage. It's an absolutely vital part of the show, and yet most of us, we don't even give it a second thought. But Isaac Newton, he did. This is how the father of modern science pictured space, as an empty stage. To Newton, space was the framework for everything that happens in the cosmos, the arena within which the drama of the universe plays out. And Newton's stage was passive, absolute, eternal, and unchanging. The action couldn't affect the stage, and the stage couldn't affect the action. By picturing space in this way, Newton was able to describe the world as no one had ever done before. His unchanging stage allowed him to understand almost all motion we can see around us, yielding laws that can predict everything from the way apples fall from trees to the path the Earth takes around the sun. These laws work so well that we still use them for the things we do today, from launching satellites to landing airplanes. And the laws all hinge on one radical idea: space is real. Even though you can't see it or smell it or touch it, space is enough of a real physical thing to provide a benchmark for certain kinds of motion, like that skater. Newton would say that when she spins, her arms splay out because she is spinning with respect to something, and that something is space itself.
Philosophers have been debating the nature of space for a very long time. What Newton does is change the terms of the debate. And with that, essentially modern science gets born.
Newton's stage was a huge hit. It enjoyed the limelight for over 200 years. But in the early decades of the 20th century, a new set of ideas emerged that shook Newton's stage to its very foundation. Ideas put forward by a young clerk working in a Swiss patent office. His name? Albert Einstein. Einstein grew up in the late 1800s, at the dawn of the age of electricity. Electric power was lighting up cities, giving rise to all kinds of technologies Newton could never have imagined. All of these developments tapped into something that had captivated Einstein since he was a child: light. Not light bulbs and street lamps, but the very nature of light itself. And it was his fascination with one particularly weird feature of light, its speed, that would lead Einstein to overturn Newton's picture of space. To see how, let's take a ride. Right now, we're traveling at about 20 miles per hour. And to go faster, all the driver needs to do is step on the gas, and the cab speed changes. Now, you can feel that change, but you can also see it on the cab speedometer or on one of those radar speed signs. Okay, you can slow it down now. But now imagine that instead of measuring the speed of the cab, you have a radar sign that measures the speed of the light coming off its headlights. That sign would measure the light traveling at an astounding 671 million miles an hour. Now, when the cab starts moving, you'd think that the speed of the light would increase by the same amount as the car. After all, you'd think that the moving cab would give the light an extra push. But surprisingly, that's not what happens. Our radar sign, or any measurement of light speed, will always detect light traveling at 671 million miles per hour, whether the cab is moving or not. But how could this be? How could all measurements of light speed always come out the same? If
you're running at a wall, it's coming at you faster than if you're standing still with respect to that wall. But that's not true with light. The speed of light is the same for everybody. That's really extraordinary.
So here's how Einstein made sense of this extraordinary puzzle. Knowing that speed is just a measure of the space that something travels over time, Einstein proposed a truly stunning idea: that space and time could work together, constantly adjusting by exactly the right amount, so that no matter how fast you might be moving when you measure the speed of light, it always comes out to be 671 million miles per hour.
To respect that absolute quality about light, time had to cease to be absolute, space had to cease to be absolute, and those two had to become relative in such a way that they slosh between each other.
If space and time being flexible sounds unfamiliar, it's only because we don't move fast enough in everyday life to see it in action. But if this cab could move near the speed of light, the effects would no longer be hidden. For example, if you were on a street corner as I went by close to the speed of light, you'd see space adjusting so that my cab, it would appear just inches long. And you'd also hear my watch ticking off time very slowly. But from my perspective, inside the cab, my watch would be ticking normally, and space in here would appear as it always does. But when I look outside the cab, I'd see space wildly adjusting, all to keep the speed of light constant. So with Einstein, time and space are no longer rigid and absolute. Instead, they meld together with motion, forming a single entity that came to be called space-time.
I think as we live our life every day, we live with a Newtonian picture of space and time. It's something that we are comfortable with. But Einstein was able to make reason conquer sense. And that really was the genius of Einstein.
This notion that space and time are unity, to me, is one of the greatest insights that has ever occurred in science. It's so counterintuitive to everything we've ever experienced as human beings.
And in the hands of Albert Einstein, this new picture of space would solve a deep mystery having to do with the most familiar force in the cosmos: gravity. Newton knew that gravity is a force that attracts objects to each other, and his laws predicted the strength of this force with fantastic precision. But how does gravity actually work? How does the Earth pull on the moon across hundreds of thousands of miles of empty space? They behave as if they're connected by some kind of invisible rope. But everyone knew that wasn't true. And Newton's laws provided no explanation.
Einstein found that no Band-Aid patches would fix Newtonian gravity. He had to invent a mechanism for it. He had to understand it.
After puzzling over this problem for more than 10 years, Einstein reached a startling conclusion. The secret to gravity lay in the nature of space-time. It was even more flexible than he had previously realized. It could stretch like an actual fabric. This was a truly radical break from Newton. Think of this table as space-time, and think of these balls as objects in space. Now, if space-time were nice and flat, like the surface of this table, objects would travel in straight lines. But if space is like a fabric that can stretch and bend, well, this may seem a little strange, but watch what happens if I put something heavy on the stretchy space-time fabric. Now, if I take my shot again, the ball travels along an indentation in the fabric that the heavier object creates. And this, Einstein realized, is how gravity actually works. It's the warping of space-time caused by the objects within it. In other words, gravity is the shape of space-time itself. The moon is kept in orbit not because it's pulled to the Earth by some mysterious force, but rather because it rolls along a curve in the space-time fabric that the Earth creates.
With Einstein, space became not only real, but flexible. So suddenly space had properties, suddenly space had curvature, suddenly space had a flexible kind of geometry, almost like a rubber sheet.
It opens up a whole new way of thinking about reality that describes the entire universe. Einstein becomes Einstein because of that observation.
Where Newton saw space as passive, Einstein saw it as dynamic. It's interwoven with time and it dictates how things move. So, after Einstein, space can no longer be thought of as a static stage. It's an actor, and it plays a leading role in the cosmic drama. Now, it's one thing to think of space as dynamic, active, and flexible like a fabric. But is it really? Is this just a metaphor, or does it actually describe what space is? Well, Einstein's theory predicts that one way to find out would be to take a little journey to the edge of a black hole. Black holes are collapsed stars, massive objects crushed to a fraction of their original size. Gravity around them is so strong that, according to Einstein's math, a spinning black hole can literally drag space along with it, twisting it like an actual piece of cloth. The nearest black hole is trillions of miles away, making it a challenge to test this prediction. But in the late 1950s, a physicist named Leonard Schiff began searching for a way to test Einstein's ideas about space much closer to home. Schiff was inspired by something we usually think of as a child's toy, a gyroscope. He thought that if space really twists, like a fabric, a gyroscope might allow him to detect it. It was a strange idea, and he chose a strange place to share it with the world. The faculty's swimming pool at Stanford. Here, in 1959, Schiff met with two colleagues, William Fairbank and Bob Cannon. He was excited about an ad he'd seen for a high-tech gyroscope. Though it looked different, it basically worked the same as the child's toy. Then and there, the three decided to launch a device like this into orbit around the Earth. Normally, a gyroscope's axis points in a fixed direction. But if Earth is actually dragging space, then the gyroscope's axis would be dragged along with it, shifting its orientation in a way that could be measured. It was a brilliantly simple plan. There was just one problem. Einstein's theories predict that the Earth's rotation twists space by only a tiny amount. An amount so small, it would be like trying to measure the height of a penny from 62 miles away. The team spent more than 2 years trying to figure out how to make such a precise measurement. They finally devised a plan to attach 4 freely floating gyroscopes to a telescope aimed at a distant star. If space twists, then over time, the gyroscopes would no longer point at the star, since they'd get caught up in the swirl of space. And in 1962, they applied to NASA for a grant, requesting around $1 million for what would come to be called Gravity Probe B. Members of the team originally thought the project would take about 3 years. They were just a little optimistic. With an ever-growing team, Gravity Probe B became one of the longest-running experiments in history. Decade after decade was spent trying to realize the original vision, which meant launching a telescope into space and building gyroscopes that were among the smoothest objects ever created.
The technology is just frightening. It was like the carrot on the front of the mule. It was like it was always 5 to 10 years away when we could do this. And it was 5 to 10 years away for about 35 years.
Consuming more than 4 decades and $750 million, the project was nearly canceled by NASA 9 times.
10, 9,
Finally, in April of 2004, the team gathered to witness the launch. Of the 3 men who sat by the pool back in 1959, only one was alive to see it.
And there we were, watching. It's a terribly exciting moment in your life. Just a thrilling experience. That was flawless. 10,000 things did not go wrong.
For over a year, Gravity Probe B orbited the Earth while the team nervously monitored its every move, trying to see if the Earth would actually twist space. Finally, the data began to trickle in, and there was a problem. The gyroscopes were experiencing a tiny, unexpected wobble, and to clean up the data would cost millions. With funds running out, it looked like nearly half a century of work was about to go down the drain. Then, at almost the last possible moment, 2 sources of additional funding emerged. The son of original team leader William Fairbank, who made a private donation, and Turki Al-Saad, a member of the Saudi royal family with a degree in aeronautics from Stanford, who arranged for a large grant. Over the next 2 years, the problem with the data was solved, revealing that the axes of the gyroscope shifted by almost exactly the amount predicted by Einstein's equations.
I think it's the first time that you can actually see Einstein's effect, his drift, with the naked eye.
This experiment provides the most direct evidence ever found that space is something real, a physical entity like a fabric. After all, if space were nothing, there would be nothing to twist.
But at the same time that Albert Einstein was investigating space on the largest of scales, another band of physicists was probing the universe on extremely tiny scales. And there they found a completely uncharted realm where Einstein's picture of space, it was nowhere to be found. Do you see what I'm talking about?
Imagine you could shrink billions of times smaller than your current size. This is the realm of atoms and subatomic particles, the fundamental building blocks of everything we can see. And when you get down to this size, the world plays by a wildly different set of rules called quantum mechanics. According to these rules, even if you try to remove every last atom and particle, you'd find that empty space is still far from empty.
In fact, it's teeming with activity. Particles are constantly popping in and out of existence. They erupt out of nothingness, quickly annihilate each other, and disappear.
In quantum mechanics, empty space is not that empty. It's full of fluctuating fields, full of all sorts of jittery things going on.
It's a place where particles are constantly fluctuating and annihilating each other and being created again and annihilating.
It's a place of chaos and bubbling.
While the theory predicted this, it wasn't until 1948 that a scientist named Hendrik Casimir suggested that even though we can't see these particles, they should cause empty space to do something we can see.
And he predicted that if you take 2 ordinary metal plates and place them extremely close together, say closer together than the thickness of a sheet of paper, then particles with certain energies would be excluded because, in some sense, they wouldn't fit between the plates.
With more of this frenetic activity outside the plates than inside, Casimir thought the plates would be pushed together by what we usually think of as empty space. And some years later, when the experiment was done,
Casimir was proven right. In empty space, the plates were pushed together. So on atomic scales, empty space is not empty. It's so flooded with activity that it can force objects to move.
And today, the quest to understand space on the smallest scale is continuing with one of the most expensive science experiments in history. This is CERN, the European Organization for Nuclear Research in Geneva. And here, buried a few hundred feet below the ground, is the Large Hadron Collider, the world's most powerful accelerator. With a price tag of about $10 billion, it accelerates subatomic particles to more than 99.99% of the speed of light and smashes them into each other. In the showers of debris produced by these collisions, scientists at places like this have discovered a whole zoo of strange and exotic particles. And right now, they are chasing one of the most elusive. A particle thought to be essential to shaping everything from the atoms in our bodies to the most distant stars. If this particle is found, it will redefine our picture of space and fulfill a quest begun more than 40 years ago. It all started in 1964, when a young English physicist named Peter Higgs suggested something about space that was so radical, it nearly ruined him.
I was told that I was talking nonsense, that I couldn't be right. So they clearly hadn't understood what I was saying.
Higgs and a few others were wrestling with a puzzle which comes down to this. The fundamental particles in the universe all contain different amounts of mass, which we usually think of as weight. Without mass, these particles would never combine to form the familiar atoms that make up all the stuff we see in the world around us. But what creates mass? And why do different particles have different masses? Try as they might, no one had been able to answer this perplexing question. Then, one weekend, after a walk outside Edinburgh, Higgs had a peculiar idea. Using mathematics, he imagined space in a new way, as something like an ocean. Particles are immersed in this ocean and gain mass as they move through it. To see how this works, think of a particle's mass like an actor's fame. And the Higgs ocean is like the paparazzi. Some particles, like unknown actors, pass through with ease. The paparazzi simply aren't interested in them. But other particles, like superstars, have to push and press. And the more those particles struggle to get through, the more they interact with the ocean and the more mass they gain. Higgs was convinced he'd made a great discovery. But when he submitted his idea to a journal at CERN, it was rejected. Undaunted, Higgs honed his theory further, until he was offered the chance to present it at Einstein's old haunt, the Institute for Advanced Study in Princeton. There, he expected his new idea would meet some of its toughest critics.
I was happily driving up the freeway, and then there was a sign to turn off for Princeton, and that really confronted me with what I was going into. I broke out in a cold sweat and started trembling, and I had to pull off the road to recover.
But Higgs persevered. It was the first in a series of talks that would convince colleagues far and wide that he was onto something profound.
Eventually, I sort of wore them down. I felt I'd sort of triumphed. So I enjoyed the parties which followed.
Today, the idea Higgs pioneered, called the Higgs field, is crucial to our understanding of space.
The Higgs field is everywhere. It's something that even in the emptiest vacuum of space has an effect. It gives you mass. So I think Higgs actually deserves credit for being one of the people that said space is stuff. It has properties in it that are intrinsic, that you can't get rid of, you can't turn them off.
The only problem? There's no physical proof that the Higgs field exists. At least not yet. But here at CERN, scientists are attempting to smash particles together with so much energy that they will knock loose a piece of the Higgs field, producing a tiny particle of its own. It's as if they're trying to chip off a piece of space.
We think that if we knock into space hard enough with particle accelerator collisions, that we can actually make a Higgs particle come out of empty space.
Our whole understanding of matter as we now have it would just fall apart if the Higgs field didn't exist.
I don't think anybody seriously doubts that we will see it. Certainly if we don't, that would be an extremely bizarre outcome.
Finding the Higgs particle would be a major milestone, establishing that the emptiest of empty space has an impact on all of matter. But it turns out that space contains an ingredient far more elusive than anything Higgs ever imagined. An ingredient that may hold the key to the greatest of all mysteries, the very fate of the cosmos. It's a mystery that began some 14 billion years ago in what we call the Big Bang. In a fraction of a second, the universe underwent a violent expansion, sending space hurtling outward. Space has been expanding ever since. For decades, most scientists thought that expansion must be slowing down thanks to the pull of gravity.
When I toss an apple up, the gravity of the Earth eventually stops it and brings it back. And just like the apple slows down with time, so too the universe should have been slowing down in its expansion because of the gravitational attraction of all matter and energy for all other matter and energy.
But that raised the question, what is the ultimate fate of the cosmos? Would space go on expanding forever? Or would gravity eventually stop space from expanding, causing it to collapse back on itself in a big crunch? To solve this mystery, two teams of astronomers set out to measure the slowing of the expansion using a novel tool: exploding stars called supernovas.
So a supernova is a star that ends its life in a massive explosion. They're extremely luminous. They can be as bright as 1 billion suns.
What makes supernova great is that they're very similar when they explode. They all get to about the same brightness and then they fade away in just about the same way.
Because the explosions are so bright and uniform, the teams reasoned that these supernovas would act as very precise cosmic beacons, allowing them to track how the expansion of space has slowed over time. The trouble is, supernovas are extremely rare. To find enough of them, Perlmutter spent years calling astronomers around the globe, begging for time on their telescopes.
We needed the biggest telescopes in the world. We needed perfect conditions. And in those perfect conditions, I would be calling people up at the middle of their night when they're trying to do some serious work, and I'd be saying, I know that you have a very busy schedule, but by any chance, if you could just squeeze in this half-hour observation, it would really be very interesting to us.
When they finally had enough data to chart how much the pull of gravity was slowing the expansion of the universe, they were in for a surprise.
The results looked a little bit strange. They didn't really show any slowing of the universe at all. Very surprising. Actually, a universe that's actually speeding up.
It was as though space, which we really thought was nothing, actually had an inherent springiness to it. And so space did not want to be compressed. Space actually wants to push the universe apart.
It looked like the universe was expanding faster and faster with time, accelerating rather than decelerating.
My immediate response was, I have to figure out why this is wrong. This can't be right.
But it was right, and most scientists converged on one explanation. There's something that fills space and counteracts the pull of ordinary attractive gravity, pushing galaxies apart and stretching the very fabric of the cosmos. This mysterious substance filling space has been dubbed dark energy, and it's turned our picture of the universe upside down.
Over the largest distances, dark energy dominates the contents of the universe, and we don't know what it is.
If you do sort of a survey, a census of all the energy in the universe, dark energy turns out to be about 70% of the universe. And up until a decade ago, nobody imagined such stuff even existed.
So in essence, the weight of empty space itself is 70% of the weight of the entire universe. That's roughly the same percentage of Earth's surface that's covered by water. Imagine we didn't know what water is. That's where we stand with dark energy.
We're really clueless about how to explain it. We have all of this fancy scientific apparatus of quantum mechanics and relativity and particle physics that we've developed in the last 100 years, and none of that works to explain dark energy.
And the discovery of dark energy held another surprise. The idea that the universe contains such an ingredient had actually been cooked up 80 years earlier.
I'll let you in on a little secret. Although he didn't call it dark energy, long ago Albert Einstein predicted that space itself could exert a force that would drive galaxies apart. You see, shortly after discovering his general theory of relativity,
his theory of gravity,
Einstein found that, according to the mathematics, the universe would either be expanding or contracting, but it couldn't hover at a fixed size.
This was puzzling because before they knew about the Big Bang, most scientists, including Einstein, pictured the universe as static, eternal and unchanging. When Einstein's equations suggested an expanding or contracting universe, not the static universe everyone believed in, he had a problem.
So Einstein went back to his equations and modified them to allow for a kind of anti-gravity that would infuse space with an outward push, counteracting the usual inward pull of gravity, allowing the universe to stand still. He called the modification the cosmological constant.
Adding the cosmological constant rescued his equations. But the truth is, Einstein had no idea if this outward push or anti-gravity really existed.
The introduction of the cosmological constant by Einstein was not a very elegant solution to try to find what he was looking for, a stationary universe.
It achieves this effect of anti-gravity. It says that gravity sometimes can behave in such a way as not to pull things together, but to push things apart.
Like the clash of two titans, the cosmological constant and the pull of ordinary matter could hold the universe in check and keep it static.
But about a dozen years later, the astronomer Edwin Hubble discovered the universe is not static. It's expanding due to the explosive force of the Big Bang 14 billion years ago. That meant Einstein's original equations no longer had to be altered.
And so suddenly, the need for a cosmological constant went right out the window.
Thank you.
You're welcome. Einstein is said to have called this his biggest blunder. But here's the thing. With the recent discovery that the expansion of the universe is accelerating, scientists are convinced that there is something in space that is pushing things apart. So 70 years later, Einstein's biggest blunder may rank among his greatest insights.
It was something that nobody else was thinking about, but it might be that Einstein's cosmological constant is the key to understanding the expansion of the universe as we see it today.
Though no one knows what dark energy actually is, it raises an astounding and troubling possibility. Einstein pictured the strength of his anti-gravity as constant. But is the strength of dark energy constant? And what if it changes over time? The answer could overturn everything we thought we knew about the fate of the cosmos.
At the moment, everything in our world, from the molecules making up my body to the molecules making up the moon, is held together by forces that overwhelm the outward push of dark energy, and that's why we don't see things expanding in our everyday lives. But that situation might not last forever.
In one scenario, dark energy will continue to push the galaxies farther and farther apart until ultimately they'd be pushed so far apart that the universe would become a cold, dark, and lonely place. In another scenario, the strength of dark energy might increase over time, becoming so strong that it would tear apart everything within the galaxies, from stars to planets to matter of all kind.
If the dark energy grows with time, then ultimately even atoms will get ripped apart when there's enough dark energy between the nuclei and the electrons to rip space apart. The Big Rip.
Our picture of space has gone through a remarkable transformation. Back in Newton's time, space was just the container. It didn't do anything at all. Then through Einstein, space begins to affect how objects move. Then with Casimir, literally objects can be pushed by the activity even in empty space. And now through the ideas of Higgs and dark energy, the very expansion of the universe may be coming from the energy of empty space itself. I don't think anybody would have thought that space would have this kind of rich and profound impact on the nature of reality.
But as far as we've come, the journey that began with Isaac Newton's picture of space as something like a stage is not yet finished.
As we examine the fabric of the cosmos ever more closely, we may well find far more surprises than anyone ever imagined. Take me, for example. I seem real enough, don't I? Well, yes. But surprising new clues are emerging that everything, you and I, and even space itself, may actually be a kind of hologram. That is, everything we see and experience, everything we call our familiar three-dimensional reality, may be a projection of information that's stored on a thin, distant, two-dimensional surface. Sort of the way the information for this hologram is stored on this thin piece of plastic. Now, holograms are something we're all familiar with, from the security symbol you find on most credit cards. But the universe is a hologram? That's one of the most drastic revisions to our picture of space and reality ever proposed. And the evidence for it comes from some of the strangest realms of space, black holes.
This is a real disconnect, and it's very hard to get your head around. Modern ideas coming from black holes tell us that reality is two-dimensional, that the three-dimensional world, the full-bodied three-dimensional world, is a kind of image of a hologram on the boundary of the region of space.
This is a very strange thing. When I was a younger physicist, I would have thought any physicist who said that was absolutely crazy.
Here's a way to think about this. Imagine I took my wallet and threw it into a black hole. What would happen? We used to think that since nothing, not even light, can escape the immense gravity of a black hole, my wallet would be lost forever. But it now seems that may not be the whole story. Recently, scientists exploring the math describing black holes made a curious discovery. Even as my wallet disappears into the black hole, a copy of all the information it contains seems to get smeared out and stored on the surface of the black hole in much the same way that information is stored in a computer. So, in the end, my wallet exists in two places. There's a three-dimensional version that's lost forever inside the black hole, and a two-dimensional version that remains on the surface as information.
The information content of all the stuff that fell into that black hole can be expressed entirely in terms of just the outside of the black hole. The idea then is that you can capture what's going on inside the black hole by referring only to the outside.
And in theory, I could use the information on the outside of the black hole to reconstruct my wallet. And here's the truly mind-blowing part. Space within a black hole plays by the same rules as space outside a black hole or anywhere else. So if an object inside a black hole can be described by information on the black hole surface, then it might be that everything in the universe, from galaxies and stars to you and me, even space itself, is just a projection of information stored on some distant two-dimensional surface that surrounds us. In other words, what we experience as reality may be something like a hologram.
Is the three-dimensional world an illusion in the same sense that a hologram is an illusion? Perhaps. I'm inclined to think yes, that the three-dimensional world is a kind of illusion, and that the ultimate precise reality is the two-dimensional reality at the surface of the universe.
This idea is so new that physicists are still struggling to understand it. But if it's right, just as Newton and Einstein completely changed our picture of space, we may be on the verge of an even more dramatic revolution. For something that's such a vital part of our everyday lives, space remains kind of like a familiar stranger. It's all around us, but we're still far from having unmasked its true identity. That may take 100 years, it may take 1,000 years, or it may happen tomorrow. But when we solve that mystery, we'll take a giant step toward fully understanding the fabric of the cosmos.
Major funding for NOVA is provided by David H. Koch and
Discovering New Knowledge, HHMI,
and by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. Major funding for the fabric of the cosmos is provided by the National Science Foundation, where discoveries begin. And the Alfred P. Sloan Foundation, supporting original research and public understanding of science, technology, engineering, and mathematics. Additional funding is provided by the Arthur Vining Davis Foundations, dedicated to strengthening America's future through education. The U.S. Department of Energy's Office of Science, and the George D. Smith Fund.